start recording.
Because the faculty meeting is beginning. So it's 10:58. Are we ready?
Yes.
Hello, everyone. Welcome to our diversity seminar. Today we have a great speaker, Dr. Pelin Angin from Middle East Technical University. We studied together at Purdue University, worked in the same research group. It was a pleasure working with Pelin. Her example is very inspirational. She's having a great academic career. And today she will talk about securing IoT networks with less data. And she will also share her experience about academic career pathway and diversity. So welcome, Dr. Pelin.
Thank you very much, Professor Dennis. So it was a pleasure to study with you too. Obviously, we did a lot of great work together with Professor Dennis Olbisha. And I'd like to thank him for inviting me for this talk today. It's really, I cherish diversity a lot. So obviously in our field, we do not have a lot of women. But all kinds of diversity is really important, basically. So, and it's a pleasure to be addressing this group today. I'll be talking about a lot of topics actually in a given time. I'm not gonna exceed an hour, so no worries about that. But let me start by sharing my screen. Well, thank you for the nice introduction too. So I'm a faculty member. I've been a faculty member at Middle East Technical University in Turkey, which is in Ankara, which is the capital city of Turkey, since April 2017. And my main field of research is cybersecurity, but when you do research in cybersecurity, you have to touch upon a lot of other fields too, obviously. So I'm focusing mostly on next generation networks like 5G and 6G. Other than that, I'm obviously, so when I started my PhD, I was working in the field of data mining and machine learning. And then I switched to systems, which I really enjoy a lot. But that gave me some knowledge to apply to the field of cybersecurity, basically. So if you want to do research in cybersecurity today, it's quite important to have some knowledge in the field of machine learning as well. Other than that, so my PhD thesis was actually on mobile cloud computing, and I still do research in the security of cloud computing today. So we've got two labs at Middle East Technical University. One of them is the first one you see here, the Meta Systems Security Research Lab is an interdisciplinary research lab focusing solely on cybersecurity. The second one you see is Meta Wireless Systems, Networks and Cybersecurity Lab, which is abbreviated as WINS. And there we do research on next generation wireless networks and their security. We have programs like 5G Scholars here, for example. So we have students trying to advance the science of next generation networks. And that's the only thing they're doing actually. So we're trying to advance these fields at the moment. So part of my research also focuses on IoT networks. Well, if you are studying, if you're doing research in cybersecurity and next generation networks, IoT is inevitable because that's why we're building those networks, right? So the Internet of Things has let us connect everything to the internet, from like even things like toasters today are connected to the internet. Right. And of course, we have many more advanced use cases like autonomous cars, for example. So the number of things that will be connected, the number of physical things, let's say, that will be connected to the internet is growing very fast. And obviously that's creating a very large attack surface, right? So these are the kinds of things I'll be talking about in the next hour. Hopefully we'll be able to go over all of these concepts. And I'm hoping these, so I know most of your graduate students here. I hope this will give you some motivation to to pursue your studies in one of these fields. So the title of the topic is Learning to Secure IoT Networks with Less Data. And this less data part is really important. I'll tell you why in a few minutes. Okay, so let's get started by looking at the promises the 5th generation of wireless networks have made to us. So these networks are different from what we're used to. And there are 3 main goals of these networks, let's say. So, and these goals are actually a little conflicting with each other sometimes. Okay, so at one edge of this triangle, we have, at one vertex, let's say, we have machine type communications, which have low data rates, high device densities, and their latency could be anywhere from seconds to hours, and they will be operating on low power. So any communication you have on these devices, between these devices, should not be consuming a lot of power because we want their batteries to last long. On another vertex, we have enhanced mobile broadband. So the peak data rates here are much higher than what we have today. And the user plane latency is expected to be around 4 milliseconds. And they're supposed to have enhanced wide area coverage. On the other vertex, we have ultra reliable and low latency communications. So this is really important because this is at the core of a lot of the applications or use cases that 5G has promised to us. So 5G actually maybe was not able to keep its promises, but those promises are moved on to 6G. Okay, so we're expecting to achieve all of this with 6G, or if that does not happen either, maybe 7G. So what we have at UR LLC is low to medium data rates, but very low latency. And these kinds of requirements are really important when you're talking about communication between cars, for example, right? So they may not be communicating a lot of data, but the latency needs to be very low. Otherwise, those applications will not be able to operate in real time. Okay, so 5G, when making all of these promises, will not be able to operate as past networks used to. So if you do not softwareize your networks, if you do not virtualize your networks, you have the same physical infrastructure. You will not, everything's operating on the same physical infrastructure. You will not be able to meet these promises you made, meet these requirements. So what people came up with actually more than 10 years ago, I think, is what we call software-defined networking. Software-defined networking is actually pretty different from the legacy networks we have in our lives today. Actually, a lot of companies, a lot of enterprises have already moved on to software-defined networks, and this is the future of networking because of the reasons I already mentioned. So if you're operating on a single physical infrastructure, you have to create virtual networks on top of it so that you can serve everybody's needs. Otherwise, with your limited physical equipment, you will not be able to satisfy all of those requirements we saw on the previous slide, actually. So what's different in software-defined networking is that the control plane and the data plane are separated. In legacy networks, these two planes are together. So what we mean by this is, I'm pretty sure most of you have taken a networks course. So what you learned there was that these routers or switches at the data plane were performing routing decisions, right? So if a network packet arrives at one of these routers, it will run a routing algorithm, and it has data that it gathers from its neighbors to decide how to route that packet so that it's going to be able to reach its destination in the most efficient manner, right? So what we have in software-defined networking are switches or routers that are much less clever than that. So they will not be performing the decisions regarding how to route those packets. The decision regarding how the packets will be routed will be performed by the control plane. So these two planes are now separated. But what we have at the control plane, which we call the controller, or it could be a number of controllers for load balancing, will be very clever. It will have a global view of the whole network below. And it will tell these routers, so when a packet arrives, if this router does not already have information about how to route that packet, it'll ask the controller being an all knowledgeable entity, will be able to tell it how to route that packet. So the only thing we need to keep at the data plane now, at the data plane routers or switches now, is a table. It's just a lookup table, which is filled with entries that were dictated by the controller in the upper plane here. And then we have yet another plane, which is called the application plane. And we could put a lot of functionality there, like firewalls, intrusion detection systems. And that is what we're going to be doing in a few slides. That is what I'm focusing mostly on in my research, actually. Okay, so in the southbound API, which is the API between the control plane and the data plane, we have the OpenFlow protocol, which is pretty standard. But at the control plane, this controller software could be a bunch of things. So there's really no standard for that one. Okay, so this is how the OpenFlow protocol operates, but I'm not going to focus on this now for the interest of time. Okay, so how would you use this kind of networking paradigm in 5G? So 5G actually consists of the core network, which is the main links that provide your whole infrastructure below, actually. And it also has the radio network, which is what wireless users connect to. So the way we design an SDN-based 5G architecture looks something like this. So we still have the routers connected with each other using a software-defined core network this time. So that means we'll have controllers dictate what happens to these packets in the core network, and this core network will be connected to the radio network through what we call backhaul links. Again, whenever a packet needs to be routed, we'll be asking, or the routers will be asking the controllers here. And I'm saying controllers because obviously a single controller will be a single point of failure, right? So actually an SDN-based network, we say, helps us secure our network in a lot of ways, but the centralization, so the legacy networks used to be decentralized, right? We're centralizing control at the control plane here. And if anybody attacks the control plane, then the whole network operation will be disrupted, right? So That's why actually, whenever you can, you should try to replicate your controllers and do load balancing in the face of things like denial of service attacks, for example, so that the operation of your network will not be disrupted. Okay, so I said SDN is a security tool because it easily gathers network usage information because it sees the whole network, right? It has a global view of the network, which we do not have in legacy networks. It can easily apply network security policies. It facilitates anomaly detection, and you can selectively block malicious traffic by changing the rules sent by the controller to the routers, right? So, and you can do this. The best part actually is that you can do this without any manual configuration need. So in the past, admins had to manually configure a lot of rules in networks, but with SDN, you're softwareizing everything, you're making everything automatic actually. So you just push those rules, those new rules to the routers, and they start performing routing in that way automatically. Also, you can direct malicious flows based on security policies. So you can observe what attackers are trying to do to your network by directing them to places like honeypots, for example. So SDN is a great security tool, but SDN can be attacked as well in a lot of places actually. So you could still attack the links between the routers. You could attack the switches themselves. You could attack the communication between the control plane and the data plane. You could attack the control plane itself. So you could launch attacks, like things like denial of service attacks or other types of attacks too, obviously, on the controller itself. And you could also launch attacks on the communication between applications and the control plane. So you have these bad guys everywhere, actually. So here we're showing just one of the types of attacks on SDN. So remember, when a router or a switch does not know how to forward the packet it receives, it'll ask the controller, right? So actually that asking happens through a packet in message. Okay, so it'll send a packet in message to the SDN controller. And then the SDN controller will decide how to route that packet, and it'll send that information back to the switch using a packet out message. So then that packet out message, its contents will be stored in the flow table of that switch. So if an attacker sends a lot of these packet in messages to the controller, and if that's the only controller, let's say, its resources will be depleted by these packet in messages. So it will not be able to respond to legitimate requests by other routers or switches, right? So this is what we call the controller paralysis attack. And it's basically a denial of service attack on the controller. So that really means even if we're using SDN in our architecture, in our network architecture, we need to do a lot of attack detection and mitigation. So this is based on the work of one of my PhD students here. What he did, or what we did in that work, is basically creating an architecture for SDN-based IoT networks for detecting and mitigating attacks in near real time. So here again, we have our data layer, which has some IoT devices connected to our switches this time. And here, obviously, in the middle, we have our SDN controller. So we use the on-OS controller in this work. And at the upper layer, at the application layer, we have a bunch of applications which achieve this attack detection and mitigation process. So what applications we have there are include statistics and feature extraction module, which means we're trying to gather data from the controller, which it pulls from the data layer from the switches. And we extract some important features that we're going to use in the machine learning model that we build based on the normal behavior of the network plus some behavior under attack. And we have the traffic classification and intelligence module here, which gathers those statistics and features from the extraction module and tries to classify that traffic based on a model we pre-built. And that model is a machine learning model, obviously. And then based on the results of that classification, a message is sent to the mitigation module, which is, so for example, as a result of this classification here, if a certain type of attack is detected, the name of that attack could be sent, right? So, and when the mitigation module receives those results, it'll decide what to do with that traffic, right? So what can it do with that traffic? For example, if a denial of service attack has been detected, it could try to block that IP from which this attack has started, right? And it could perform a lot of other operations, like I said, like redirecting that traffic somewhere else so that it could be analyzed in more detail. So this upper part, like the applications and the controller, were run in a Kubernetes platform in this work, because Kubernetes provides some desirable features like automatically replicating the controller instances when needed. And so this is the kind of structure actually. So when you think of 5G, we're talking about virtualizing a lot of things, right? So 5G and 6G come with a lot of virtualization, like in the case of network functions virtualization, right? So in the past, we used to have our network functions like firewalls, like intrusion detection systems, running on dedicated devices, right? But now with 5G and 6G and beyond that, we'll be running all of these functions, all of this functionality will be running in the cloud, right? So it makes a lot of sense to build this kind of architecture in the cloud, actually. Okay. So now we're switching context a little bit here. So we said if we go back and look at this traffic classification and intelligence module, we're talking about some machine learning or deep learning algorithm here, right? So some algorithm we built based on data we were able to gather in some state of this network below, right? So the biggest problem, if anybody here is working in the field of machine learning or deep learning, they'll know that the biggest problem with these fields is being able to find quality data, right? Especially if you're running deep learning algorithms, if you're trying to build deep learning models, finding sufficient data for those models, sufficient and quality data for those models is very difficult, right? And also, people do not want to sit down and label a lot of data. Even my students do not want to do it. So data is a big problem today. And unfortunately, when you're in the field of cybersecurity, you will hit this wall where most companies do not want to share data with you because, like, if they share the kinds of attacks that took place in their network, for example, they will be sharing their secrets with you, right? So you will be seeing what vulnerabilities their network has, right? So data is very sensitive. Data privacy is very sensitive everywhere, obviously, but also in the field of cybersecurity. And then what do you need to do? You need to create your own data and label it, right? And that's a daunting process. So nobody wants to do that. The same thing applies actually to other fields like computer vision, for example. So you're trying to learn a model for distinguishing between cats and dogs, let's say. You need a lot of data, right? And actually, I think it was first in the field of computer vision that people came up with this idea of trying to create models, trying to create algorithms that would be able to produce good models with only a few data items to learn from, with only a few training data items. And actually, if that few is equal to 1, that's what we call one-shot learning. And if one sample is not enough, you need a few more samples, but not a lot. That's what we call few-shot learning. Okay, so if you're able to learn the representation of a cat by just training your model on a single instance of a cat picture, that's what we call one-shot learning. But obviously, one-shot learning may not give you perfect results. It will not give you perfect results, actually. So you might need a few more instances. And the same thing applies to the field of cybersecurity, right? So if you have one instance of an attack traffic, that's not going to give you good results in all kinds of diverse cases, right? So what we did in this work was to build few-shot learning models that we took from the field of computer vision and applied it to our field, where we use few-shot learning algorithms from the literature, where we have what we call a support set, which is like the training data for your algorithm, and the query set, which is like the test data. So how few-shot learning works is basically you give it these few examples of each different class in your classification task. And when you're at the training time, you give this query sets examples, and it learns to map these into a metric space based on their distances to the items in your support set. Okay, so anything in this embedding space, which is closest to these 3 examples of denial of service attacks, for example, then any of the other clusters you see here is classified as a denial of service attack. So actually, few-shot learning algorithms have the same representation, so they still use a deep learning architecture, but they are able to learn better models by just including a few training data items in the training set. The prototypical networks is just one example of a few-shot learning algorithm, and that's what we used in our work. So here you see convolutional neural network blocks. And this is what you would be using in a typical deep learning algorithm for this classification task, right? So this is what we call the embedding network. So you precede this with the pre-processing stage, and you input the results of the last CNN block into a distance metric to be able to map it into this embedding space. And then that gives you class likelihoods for the different classes, and whichever is the highest likelihood, that instance will be assigned to that class. Okay, so how do we do attack detection using this kind of machine learning model, let's say, or this kind of like end-to-end architecture? Well, so obviously we extract the features using this statistics model. Let me see if we have examples of the features here. Well, we do not have examples of the features here, but any data set you find on like attack detection or intrusion detection, there are a lot of data sets today, obviously. They look at the same types of properties. So the IP, the source and destination IP addresses, the source IP ports, the duration of communication between those endpoints, the number of bytes, and similar, like a lot of other features. Okay, so the way we perform attack detection here, so obviously we said we will be using these models, few-shot learning models, when we do not have sufficient training data, right? So if you already have a lot of training data for the different classes of attacks and normal traffic, you do not really need to use these models, right? And that is actually why we create an ensemble of what we call protonets, which stands for prototypical networks, with SVM, support vector machines, which is a well-known machine learning algorithm that has achieved good performance in a lot of intrusion detection or intrusion attack classification tasks. We create an ensemble of those so that when we do not have sufficient training data, we will be relying mostly on the results of the protonet. But if SVM is already performing well, we will be relying on the results of SVM mostly to classify different flows in our different network flows in our network. Okay, we already talked a little about attack mitigation. So if the network flow coming from one specific IP, for example, looks like it's classified as a denial of service attack repeatedly, then you can just block that IP, right? So it may not be wise to directly block it at the first instance when your algorithm classifies it as an attack, because it may not be an attack, right? So these algorithms are not bulletproof. So if the algorithm repeatedly classifies it as an attack, then it might be, that could mean that there is really something wrong going on there. So you install your flow rules accordingly. So this is what you do when you're doing flow rule updates in your routers, basically, or your switches. And these flow rule updates will be issued, will be sent by the SDN controller. They'll be pushed from the SDN controller to the switches and routers in the data plane. Okay, so for example, in part A here on the left, we see a packet redirection flow rule update, whereas on the right, we see a flow rule update for dropping packets, right? So you see that on in the actions part here. Okay, so this is what our complete embedding network looked like when we did our experiments. Obviously, so there are a lot of parameters here still. Like when you're doing experiments with deep learning architectures, there are a lot of parameters you need to play with, right? And so here our convolutional layers consisted of these settings. And anytime you run these classification algorithms in intrusion detection domain, you have this confusion matrix. So whether you classify attacks as, you correctly classify attacks as attacks, or you misclassify attacks as normal traffic, or whether you correctly classify normal traffic as normal traffic, or you classify normal traffic as an attack. So we use the precision and recall metrics, and the other metric that's commonly used in this kind of research is the F1 score, which is obtained by using a combination of these, not a direct combination, but some function of these. Okay, so we did experiments because we're focusing on IoT here. We needed a data set that has IoT traffic in it, right? So maybe the biggest thing missing in today's intrusion detection data sets is that, so there's a lot of IoT traffic around today, right? And the data sets people use in their research today are mostly built based on legacy networks. And that's not going to satisfy, that's not going to give us a realistic picture of what we have in the IoT networks of today. Okay, so that's why we use this bot IoT dataset, which is based on IoT traffic. This is not a dataset we created. This is an existing dataset that's public. So if anybody is interested in running experiments on IoT traffic, they could just use this one. So it consists of these categories of attacks. And so obviously there's an imbalance here, which creates a bias when you build your machine learning model. That is why we extracted a smaller part of this data set in which we tried to equalize, or at least create similar numbers for the different classes. Okay, so we see here that Proto-S, which is our ensemble model, was pretty successful. So what we need to look at here actually is the number of training samples for each class that we used to train the model, right? So for example, CNN here, the convolutional neural networks model, is achieving an F1 score of 0.57 when it's trained using 100 samples of each class. But when you use 1,000 samples of each class, then CNN achieves the best performance, right? So, but for our Proto-S model, for example, is achieving a similar performance for all cases, right? So that really shows us that this few-shot learning model is really doing its job properly. So it's really achieving what we wanted. Okay, so these are the class-based results, but I'm not gonna go over those because I don't want to run out of time before I complete this talk. So there's another data set, UNSW NB15, which is So everybody working in this field actually knows the KDD CUP 99 dataset, which is one of the oldest intrusion detection datasets, I think. But it's been criticized a lot recently because, well, obviously it's a very good dataset, but it's not really modeling today's networks, right? So, and people in various places at various universities try to create other data sets. And this is one of those data sets that a lot of people are using in their research today. So again, we had to do some extraction. So this data set also has a lot of different types of attacks in it, but we had to extract some of it because the numbers were not really compatible, right? So, and like, if you have very few instances of some of the attacks in your data set, that class will be underrepresented. So we just got rid of those classes. Okay. So here we see actually similar performance. So if you look at CNN, for example, if you give it 100 training samples for each class, it will not perform that well. Its performance increases a lot when you give it 1,000 training samples. By the way, this is not IoT data. So we just used this data set for sanity check of the few-shot learning model. So the performance of our model, again, increases obviously with more data, but the change is not that dramatic. Okay. So these are the precision recall, F1, and accuracy scores for 100 training instances. And these are the class-based results. So what we did last in this work was to create our own SDN dataset because all the other datasets that we used were not SDN traffic based. And SDN traffic, although it's similar to the traffic of legacy networks, it still has some differences. Some of those features are not easily extractable in SDN. And if you want to operate in real time, it becomes difficult if you're not able to automatically extract those features. So what we did was to create an SDN setup in our lab and mimic the behavior of IoT devices to record traffic that would be used as training data for our model. So we have some evil hosts, we have some benign hosts, and we have some IoT devices. Okay, again, in this setup, our model achieved the best results. Actually, we trained all of the models with even more samples, 10K samples. And then, only then, CNN was able to outperform our model. So these are the detailed scores. And these are the scores for the different classes. You'll see that in most cases, for the different classes, the detection rate is much better with the Proto-S model. Okay, so now we're switching from the machine learning part to more network related stuff. So our controller needs to be scalable, right? Because all the traffic will be passing through the controller in all the cases where the routers do not know how to route the traffic, for example, right? And the control plane is what provides communication between the application layer and the data layer. right? So if the controller is not scalable, it will not be able to handle all that traffic. And that's very important when you're building huge networks with a lot of IoT devices connected, for example, right? So to be able to provide that scalability, we used the Kubernetes platform, which was able to automatically create replicas of the controller instances. And also, obviously, so whenever you're doing intrusion detection research, it's not sufficient to test the offline performance of your models, right? So you need to actually create an actual network and do other measurements, like whether the integration of your security protocols or your security measures is hurting the real performance of your network. If it's slowing down anything, if it's causing the loss of any network packets that are not supposed to be lost, right? So we tried a few scenarios. So in the first scenario, for example, there is no attack and no security mechanism. There's just normal traffic. And we record the performance of the network in terms of whether any packets are lost, the packet rate, and latency. And we could use obviously other measures too. In the second scenario, we had some attacks, but no security mechanism. There's also normal traffic. There's normal traffic in all cases, obviously, right? There's always going to be some normal traffic in your network. In the third scenario, we had no attack. We had attacks. No, we had no attacks, but the security mechanism. So the purpose of the third scenario here is actually to measure the overhead that's caused by the security mechanism on your network, right? So if it's causing any degrading of your network performance. In the last scenario, we had attacks, we had our security mechanism, and we also had normal traffic. Obviously, in this last scenario here, we're trying to see whether our security mechanisms really doing its job well, in the sense that if it's able to prevent packet losses. And so this is to be compared with the second scenario here, actually, right? So if the network is under attack and there's no security mechanism, what happens when we integrate our security mechanism in the presence of attacks? And we tried different topologies, different network topologies here. So what you see here is that obviously the time to block attacks is really important too. So if you detect an attack after it's too late, you cannot do anything, right? So you should be able to detect these attacks in near real time. So that's one thing we measured in these experiments. So time for first detection, for example, on different ports varied from 47 seconds to 60 seconds. And time to block that traffic varied from 79 to 77 seconds. So in the different scenarios here, we looked at the throughput, which is measured in packets per second. And you see here that if you compare scenario 2 with scenario 4, you'll see a big difference, right? So in scenario 2, we have some attacks which results in a very high packet loss rate, right? Whereas in scenario 4, the packet loss rate is much less, and the throughput, the number of packets per second, is much higher. So you might be wondering why we have like 0.13 packets per second. That's really because this is IoT traffic, right? So IoT traffic could be it really depends on what type of IoT network you're modeling. But if you're talking about these very small devices that only send data every once in a while, you will not be sending a lot of packets every second. We did similar experiments for a 3-switch topology, and the results are similar. So that showed us our approach is working quite well. So this is the end of my presentation. Thank you very much for your attention. And if you have any questions, I'd be happy to answer them. I hope this was not too fast. I tried to finish on time and save some time for questions too. The questions could be about anything, by the way, so it does not have to be about this presentation or my research.
Hey, I have a question. So what is the future of your research? Like, where are you going next?
Yeah, that's a really good question. So actually, I'm working on a bunch of different topics right now. And so we're writing a new project proposal on building smart cities. That's something we want to build in probably in Ankara here. And that has a lot of different components, like autonomous vehicles, smart grids, smart buildings. And actually, all of these different components have a cybersecurity component in them. So I really find the field of cybersecurity very rewarding in this sense, because there's always going to be, no matter what system you build, there's always going to be people trying to attack those systems. And like your research is never blocked, because you have to keep fighting against those attackers to build new protocols, to build new systems that'll keep those future systems safe and secure, basically. So I'm working on smart grid security. I'm working on 5G and 6G security. Autonomous, like vehicle-to-vehicle communication security. Those are all things I'm interested in, and I think I'll be working on in the next decade, I'd say.
Well, this is really very interesting. Is there anybody else that has a question? And if there, you can write it in chat as well, and I can read it if we need to do that. Okay, yeah. Can you see the chat, or do you want me to read?
I believe you said on one of your algorithms that the dataset results were very minimal after a certain number of data points. Does this seem to be an issue in your research? So actually, what we expected to see, and the reason we did those experiments for like different number of training samples, is that we actually expected to see that difference. And we knew that our algorithm, our few-shot learning algorithm, would not be able to achieve that high performance other algorithms would be achieving when given a good number of data points. So we do not really see this as an issue with our research with few-shot learning algorithms, because you could always offset for that using ensembles with other models that achieve good results when given a sufficient number of data points. Does that make sense? Or does that answer your question? Okay, thank you.
Is there anybody else?
What's an example of an anomaly you may find? So something like a denial of service attack, for example, where your network is receiving much more traffic than it normally does, is an anomaly. Or if somebody is trying to access ports on your server, for example, that are never used or that they seldom access, that's an anomaly. So there are many kinds of anomalies, I would say, but these are just some examples. And so actually, you do not have to use classification algorithms actually to spot anomalies. Things like, for example, one class SVM will tell you what is not normal in your network. So if you train your models to learn the normal representation of your network, and like at test time, you give it examples that do not look anything similar to what they learned during the normal operation time, those will be classified as anomalies in your network. Does that make sense? You asked for examples, but yeah, so I think I tried to give 2 examples. Thank you.
All right, our students have class at 12 o'clock.
Oh, okay.
So some of them are probably have already left, but thank you so much. I just appreciate your time. And this was a great end to our seminar series. But thank you for your time, especially at night for you.
Well, thank you very much. It was a great pleasure to be with you. Well, hopefully in the future, I would be able to visit the department in person too.
Yes, that would be wonderful. That'd be great. All right, well, have a good rest of your night.
So have a great day.
Thank you.
Bye.
Bye.